All right, so welcome to the last lecture of this course. Today there will be no new material. It's basically just a short recap of what we have done, pointing out a few important things, talk a little bit about the exam, and so forth. So let's get to it. The exam is next week sometime, Thursday, I believe. You should check this, not take my word for it. The idea is that, what I like to do in an exam is to have problems which are focusing on understanding rather than memorization. So you don't have to, remember how many bits there is in an Ethernet header and things like this. However, one should know what an Ethernet header is for, where it fits into different things and so forth. So there is an element of learning the terminology, obviously, so one knows what is asked for and what we talk about, but maybe not the nitty-gritty details in all the protocols, how many bits are allocated for sequence numbers and in Ethernet, for instance. That is not super important, right? So what you can bring to the exam is like a Chalmers approved calculator. So this is basically so you can, it won't be any advanced mathematics in this, in the sense that you need to do very complicated calculations on a calculator, but you might want to do ratios, maybe a square root or a log or whatever, right? So anything super basic would do nicely. You can bring your math handbook if you like. And then you can bring your own handwritten notes. So on both sides of one single A4 page, no photocopies, right? And no other students' notes are allowed. So please do this by yourself. And the reason why I want you to write this, what should we call it, cheat yourself, is because it's a good learning experience to do this, to summarize the course basically. And why it's handwritten here is just because we don't want people typing in this and then shrink it down so you have like micro text on a whole A4 page. That's not really the intention here either. So exam questions will be in English. Answers in Swedish are okay, but I really would be super happy if you do it in English, because it will make it easier for Schweib to correct it, right? But it's okay to do this in Swedish if you're not comfortable with English. 4 problems, 48 points. Passing score is 20 points on the exam. So you need to pass the exam as part of passing the course. Then you also need to pass the project. And if you pass the project and the exam, then you get a passing grade. And the final grade is then based on everything that is accumulated, the exam, projects, quizzes, and so forth. Maximum is 100, and then the grades are according to this table. So it is possible to get 40 points or more without passing one of the two things, and then there is still not enough for a passing grade. Okay, learning outcomes. So these are in the course PM and so forth, and I typically print them out and have them beside me when I design the exam. So this is something that I actively look at. Okay, so not every exam obviously is not going to cover exactly everything here, right? And it's also a little bit fuzzy what is meant by these, but these are my guidelines when I design the exam, and maybe this could be also your guidelines when you study for it. So I'm not going to repeat everything. You find that in your course PM. There will be a course questionnaire, a web questionnaire as usual after each course. Super important for us. So, we take this very seriously. We go through that and look for things that we can improve from year to year. So whatever is good in the course is likely to somehow have been affected by students, or is at least partially a result of student feedback. Now, previous years, if you talk to earlier year students, we awarded 2 extra points on the exam for filling out the questionnaire. Now, however, last year we were told that this was against the rules. Yeah, so we can't continue with that, essentially. So I'm sorry for that. It was not my decision. I would have liked to keep on doing this. But I hope that you can nevertheless find it important enough to fill out the questionnaire with your constructive feedback. So that would be really, really good. During the course, we also have had meetings with the student representatives, and one concern that was asked for is whether old exams used a notation or terminology which is different from this year's, because we changed the book. So that's a good question. So I went through the exams briefly and couldn't find anything really that stood out, right? So there will be, maybe a letter M is N and something like this, but it should really be self-contained from the text, right? So it shouldn't be too hard to, there is no drastic change. Okay. So I think you're good to go there, right? You can look at all the exams and get a good feeling for what I think is important in the course. Now, having said that, all the exams is a really poor indicator of what's going to be on the next exam, as you would see. They differ quite a lot in the topics which are covered, in the way the topics are covered, right? So it's not like a standard problem on medium access, for instance. It varies from exam to exam, but as long as one knows what's going on in medium access, there is no problem. Should be no problem, I hope. Okay. So now, with that, are there any questions on exam rules, things like this? You've taken many exams before, so it's nothing special in that sense. So then I thought we would do like a brief overview of the course. I'm a little hesitant to do this because then there are so many things which I cannot possibly talk about within the time we have, because I mean, how can you summarize a course during one lecture? It's difficult, right? You're bound to miss out on something. So if you want to have a complete review of the course, then look at the exercise problems, look at the lecture slides, maybe review a video if you're unsure about what is meant on the slide. Look at the recommended reading in the textbook. The textbook is I think quite good in the sense that it explains things really well. There are a few minor typos here and there, but that goes with every book, I would say. The most serious one is the way how selective repeat was presented, because there is a bug in that algorithm. But if you look at the that lecture slide, the week after I presented selective repeat, there is a fix to this bug, right? So if you want to get that correct, do that. Okay, so then let's just dive into the material here and see what we end up with. So at the core of the course, I would say the idea about layers and protocols and services. So this is how we specify and how we think about communication systems. So there is this OSI reference model. It has a couple of layers, 7 in total, and the layers have different tasks, right? So this is the way it's sliced up in the OSI model. There is another slicing for the TCP/IP model, but it's not fundamentally very different. So I think one should have a good understanding of why layers are there and what they do, right? Both the OSI and TCP/IP models. So in practice, for instance, for the OSI model, the top 3 layers are typically bunched into one layer. So here I think when you study for the exam, you should be able to say what the application layer does, what the transport layer does, or data link and physical layers, right? You don't necessarily have to know exactly what the presentation and session layers do. Okay. And this slide, I guess, summarizes quite a lot of what's going on in these layers. So this one is a nice thing to look at and try to figure out, okay, try to explain this to yourself or to your buddies. How does this really work? We have layers, they have numbers. We have something like, think of this as a small computer program, a process running at one end, one node, and a corresponding peer process on another node. Okay, so these are more or less identical software programs, or at least they have an identical functionality. And what they do, these entities, they exchange data back and forth to execute a protocol. And they do that by sending these protocol data units back and forth here. So this is the virtual communication of the protocol data unit. And by sending this information, these two entities can provide a service for the layer which is above it. Okay. So for instance, layer n here provides a service up to layer n+1, and layer n+1 provides a service to layer n+2. Layer n+1 provides a service by using the services of layer n. So you use the services below to provide something up in the stack. One thing of common confusion is that these protocol data units that go back and forth here, physically they are transmitted using the layer below it. And when going over the layer boundary here through this imaginary software construct, which is called the service access point, think of this as an application, programmer's application interface, some function that you call with some parameters. And what you do, for instance, you send down the payload that you would like to be sent. And then there is some control information, addresses, other things, right? But anyways, in this slide, we only have the data that's pushed down here. And once it pushed down here, it changes names from a protocol data unit to a service data unit. So from the perspective of layer number n, it gets data from above, and this is the bits that the service that layer n provides to the layer above it should transmit. So whatever bits we get down here, we think of that as a service data unit. And then we, in layer n, constructs a protocol data unit, which consists of the service data unit and some headers. Okay, so this is what's going on in each of the protocols, protocol layers. And this is called encapsulation. So this encapsulation is an important principle on how we construct protocols, that the protocol on a certain layer here should, the control information and how to execute that is carried in the header information. This is the control information, and this is the payload. And the protocol here should never decide its actions on data which is in the service data unit. So this is treated as a black box. These bits, you should never really go into that and decide something to do. The only thing that matters is the number of bits, basically, right? You need to make space for them in the protocol data unit. But that's it. Okay, and then data that goes down here eventually goes up the other way. And then you strip off the headers as you go up. Okay, so this is a super important mental model for how protocol works. In practice, there is some cheating, right? The interfaces are not so clean, and sometimes you violate the rule that you should never look into the service data unit here to decide what to do and so forth. But at least from a principle point of view, this is what we would like to do and how to construct protocols. Okay, and then we have these reference models. We have the OSI model. Again, we have the top 3 ones, which are typically bunched together into the application layer. And then we have the transport layers, and then network, data link, and physical. And here we have now introduced that we have 2 end nodes one here and one here, and then some network in between with routers, switches, whatever, right? A bunch of different things. And inside the network, the protocols which are active inside the network is network protocols, data link protocols, and physical layer protocols. So these are implemented, perhaps not all of them in all nodes, but at most these three. The transport layer is implemented in the end nodes. So there is transport layer here at one end and transport layer at the other end. So there is no transport layer inside the network, in the routers and so forth. It's not part of it. So we call the upper layers here end-to-end protocols, and maybe these should call then hop-to-hop or link protocols, or whatever you want to call it. But it has at least between an end node and a router and to the next router or to the next router or switch or whatever it is here, and then the final hop from the final switch or router to the end node here. So end-to-end protocols, and these are not end-to-end protocols. Meaning that there is a software program running in this computer, in this one to implement the network protocol, and this one to implement the network protocol, and this one into the network protocol. So we have many computer programs that are communicating with each other in order to enable the functionality needed for the network layer. Okay, then encapsulation, we talked about that. So when we go down the stack, we add headers and sometimes also trailers. Okay, and then when we go up the stack, we strip them up as we go along. The relationship between the OSI model and the internet reference model is not super one-to-one particularly clear. And the reason for this is that the TCP/IP model is something that has been evolving over many years. It started as a research project maybe in the 60s, and then these ideas about layers and protocols and so forth were not so crisp at the time. So it was implemented and fixed and patched and added, amended, tuned, and so forth. So it was organically been evolving into what we have today. While the OSI model is a thought-out model from the beginning. So this is a clean model, and this is a messy model. The messy model is used in practice. The clean model is not used in practice. Right? So it's just the way it is, I guess. The thinking came after the implementation. Okay, and then there is no direct, for this reason, there is no direct connection between these layers and these layers, even though they're called the same in the book here. But if you look on the internet, for instance, some books think of the TCP/IP model not being 5 layers, but 4 layers. Right, so not even the number of layers is universally agreed upon in the TCP/IP model. Okay, now a little bit of efficiency of layers. We'll get back to this a little bit later also, but the prime idea is that the layer, the rationale for the layer, the only purpose of a layer is to provide a service. Okay, and it provides a service for the layer above it, and it does that by using the services of the layer below it. So that's the principle. Then one can think about how efficient is this implementation, how efficiently do we implement this service. One can measure that in different ways, but the way we do it in this course I've been concentrating on is to look at the effective rate, which is the rate which we deliver in our servers. Okay, so let me try to explain this again. So layer n provides a service to the layer n plus 1. Okay, so the rate which is experienced by layer n plus 1 is the effective rate. So the effective rate is the number of bits in the layer n service data unit. So this is, if we layer n, the number of bits we get from above is the number of bits in the service data unit. Okay, then it takes a certain time to deliver that to the other side. Okay, And the ratio between the number of bits we get from above divided by the time it takes to transport this to the next node or across the network or whatever, that is the data rate which is experienced by the layer above us. Okay. One can also write this in, since the layer n service data unit is also the layer n+1 protocol data unit, one can think of this in terms of the protocol data unit. But these are the same, right? It's the same thing, right? It's just two different names for the same thing. Okay, now the efficiency then is of the layer is the ratio of the effective rates. The effective rate we get from the layer below us to the effective rate that we provide to the layer above us. Okay. And this number is always less or equal to 1. It cannot be. We cannot create more data rate than the layer below us provides to us. Right. Okay, TCP/IP protocol suite. On application layer, we have a bunch of protocols. We talked about a few of those. On the transport layer, we have essentially 3 protocols. On the internet layer, we have one main protocol, IP, and then a couple of helper protocols here. That's only to make IP work, basically. But IP is the main thing. And on the network layer on the data link layer and physical layer, we have a bunch of different protocols. So UDP, best effort, connectionless datagram transfer service. TCP, reliable, connection-oriented, full duplex stream service. SCP, reliable, connection-oriented, multi-homing, full duplex multi-stream service. If you're unsure about what these things mean, go back and look at the slides. We don't really have time to talk about that now. Then we talked about, okay, so if we go back a little bit to the OSI model, if we talk about the physical layer here, there exists a specific model for the physical layer also, and that's called the Shannon communication model here. So I would say that these things here is physical layer stuff, while this source encoder is more, actually it's the presentation layer, but let's call it the application layer. So it's not strictly a model of the physical layer, but we typically think about that as such. And as a matter of fact, we haven't talked about this functionality in the course at all, what it does. But essentially, it's data compression. So we have some bits, and then we compress it down to fewer bits. Think of this as maybe you take a text file and you make a zip file out of that, or an MP. You record some music and you make an MP4 file of that. That's also source compression, data compression. So, and then we have a channel encoder and modulator, and these have different purposes. This one is to correct errors that occur on the channel, and the modulator is to convert bits to a waveform which is suitable for the channel. Then we have some noise on the channel, and demodulator and channel decoder is the inverse functionality of the transmitter blocks. And hopefully we have some bits here and we have some bits here, and hopefully these are equal, right? They are not in practice. The probability that the transmitted or the decision on the ith receive bit is not equal to the transmitted bit here. This is called the bit error probability. Okay, this is something that we would like to make low, small, but it's never 0. And to handle these remaining errors that the physical layer still produces, we use error control mechanisms on the data link layer to handle these, and actually also on the higher layers. So error control is made at various stages in the protocol stack, not only at the physical layer. So the combined effort of controlling errors is typically needed for end-to-end reliability. Okay, so the main tool we talked about for physical layer modulation is this pulse amplitude modulation. I won't go through all the details here, but this is something that you should be familiar with. If you feel like this is strange, then read up on that a little bit. But essentially what's going on is that, essentially what's going on is that there are bits coming in and there are waveforms coming out. So this is the function of the modulator. And the data rate, the number of bits per second that we can transmit, depends on how many symbols per second we can transmit, and then how many bits there are per symbol. So the relationship between the data rate and the symbol rate is through these equations. Now, how fast can we transmit? Well, it depends on the channel and on our waveforms. So a common receiver looks something like this. We have now the symbols that we would like to transmit. We have some transmitted signal, there's some noise. So the received signal is sum of what is transmitted plus noise. Then we filter the received signal and we sample it, and then we get some discrete thing here. And obviously ideally we would like yk to be equal to ak. That would be nice. That's the goal, right? Now, if one looks at yk, it turns out that it is indeed equal to ak times a constant. So maybe we should be okay that if it's ak times a constant. That's fine, right? We can just divide by the constant and then we have the data that was transmitted. So this is fine for us. So if one looks at if we ignore noise to start with, the output is equal to the input A that we care about, and then some stuff that we don't care about. As a matter of fact, we think of this as the interference. And the interference, since it's due to other symbols, we call that intersymbol interference. And this mysterious function H is the convolution of G, the transmit pulse, and F, which is the receiver impulse response. Now we can get rid of this, which is our goal. We can get rid of that if samples of this H signal at symbol rate. So T here is the time between symbols. So if we sample that at symbol rate, if it's 1 when n is equal to 0 and 0 otherwise, it's fine, because then we get rid of this, and then the constant we have here is actually 1. Okay, then because if h of 0 is equal to 1, then the constant we have here is 1. So this is desirable. And we can do that by imposing this requirement on h in the time domain, which turns out to be this requirement in the frequency domain. So capital H here is just a Fourier transform of the time signal h of t. And the implications of this is that if we have a pulse g, which has a duration which is less or equal to t, the time between consecutive pulses, then we will have ISI-free transmission if f also has support less or equal to t. So that's one option. So this is option 1, right? The other option we have is this, when the pulse has a certain bandwidth. Okay, so it doesn't it's constrained to have a certain bandwidth. Here it's limited in time, here it's limited in frequency, and we cannot be both, right? So we have to choose either we time limited or we band limited. Okay, we can't have both. So for option 1 we know what to do. For option 2, when we band limited, which is the interesting case in practice, what should we do then? Well, it turns out that if the symbol rate is too high, we're out of luck. Okay, so if the symbol rate is more than twice the bandwidth, then nothing we can do. We will have intersymbol interference. If the symbol rate is exactly twice the bandwidth, then it's possible to be ISI free, but only if and only if the convolution of G and F is this sinc function. So then we need to design G and F in such a way that we get a sinc when we convolve them together. One way to do that is to choose G and F to be that sinc. then actually that works out. The sinc is a very peculiar function in the sense that the sinc convolved with itself becomes itself. Very few signals have this property, right? Okay. So maybe I should write this. So F and G equals sinc works well in this case. There might be other choices also, but this one works at least.
What happens if we use root-raised cosine pulse?
Yeah, so let's get to that in a second, right? So the next choice is when the symbol rate is less than twice the bandwidth, then we have some flexibility, and then we can use root-raised cosine pulses for G and F. Okay, so here there are many choices of G and F that works. And if the convolution of this is this HRC, okay, which is a signal with the root-raised cosine spectrum, which is this. So I didn't put this in the time domain. So one possibility in this case is to choose G and F as root-raised cosine pulses. Okay, and the root-raised cosine pulses, maybe I should write this here. The Fourier transform of the root-raised cosine pulse is, not very surprising, the square root of the raised cosine pulse, like this. Okay, so to get G and F, what we can do is we can take this function, take the square root of that, inverse transform that, and then we have G and F. So that's how to do that. I mean, if you go back, there is you don't have to do this obviously at the exam, right? And or rather, there is no need to memorize the time domain expression for the raised cosine and root raised cosine pulses. Because we won't use them. However, it's nice to know what is the bandwidth of this raised cosine, which is also the bandwidth of the root raised cosine, because it's only the square root that differs them. And the bandwidth is 1 plus alpha over 2t. Okay, and this alpha is something that we tune. Alpha is a number. Alpha is a number between 0 and 1. So that, which means that we have a family of pulses here. So essentially, if we have a certain bandwidth W, then we put this equal to W, and that gives us the alpha and t, or the possible combinations in alpha and t that fulfills this. Yeah. Okay. So if we continue here then, if we then look at this receiver blockchain again, and here there is like a change of notation from the G, the transmitted pulse is now called H. So sorry for that, but that's how we presented that in the course, and I'll keep it here. And the root reason for this is that the book does this, right? So yeah. It's a little bit confusing, but maybe it would be even more confusing to do what the book does not do. So I chose to do it like this. So anyways, it's the same thing. So now we have H is the transmit pulse, but we also select the receive filter here to be matched to H. So this is the matched filter to H of t. Okay, and so if we do this, we get Y, we sample at symbol rate, we get some Y, and then we actually scale this with 1 over the energy for H, and then we get Z. Okay, and ideally, Z is equal to A. Okay, so this is the goal, and that means that Yk here is equal to the energy of Y times AK. So that's the goal, right? So, and by taking EH times AK and divide by EH, we get Z, and then Z is equal to AK. So that would be nice. And as a matter of fact, if there is no noise, in the ideal case, this works as long as H convolved with the impulse response, which is also dependent on H, is a scaled Nyquist pulse. Question?
The CK,
Yeah?
should it be AK or S of T? What does the last bit? The A hat K?
Aha, okay, so let's get to that. So A hat K is the number in the symbol alphabet which is closest to the input.
And that's not the AK?
It is AK. If the input is AK, the output is also AK. Yeah, okay, so the goal then, this one becomes AK.
So the goal is for CK to be A at K as well?
Let's start. I mean, we want the decision here on AK to be AK. Right? And one way to ensure that is that the input is also AK. And if the input is AK, then YK should be EH, the energy for the pulse, times AK. So going backwards, we see this. And we can ensure this expression, we can ensure that if the H is a scaled Nyquist pulse. Okay. So it's actually the same as we had before, is that we would like the impulse, the pulse that we use convolved with the impulse response should be a Nyquist pulse. Okay. Here we allow this also to have a scaled Nyquist pulse in the sense that we can any scale factor we can have on this, you multiply this with 15, it's okay still. It's the shape that we are concerned with, not the actual amplitude, because we compensate for the amplitude here. Okay. So did this answer your question? Pretty much?
Yeah.
Okay, right. So obviously the goal is that the output of everything should be equal to the input, because then we have perfect communication. And if this, one way to ensure this is that CK is actually equal to AK. Right?
But isn't AK in the beginning bits and AK in the end is symbols?
Yeah, so here, what is not printed here is that we have a mapper with the bits coming in here. And if we then take this and we do demapping, oops, that was ugly. Demap, like this, we get our bits like this.
But isn't the PAM block the thing that makes bits to symbols?
Yeah, so I just simply didn't draw these things out. But the whole thing from bits to bits includes also a mapper. But
isn't the PAM block the...
no, the PAM block only takes symbols, amplitudes in,
Okay.
and then outputs a signal, given a pulse shape and the time between these pulses. Yeah. So the PAM block does not include the bit to symbol conversion. Yeah. Okay. Now, what could possibly go wrong here? Well, it depends on the noise, obviously. So the noise is not zero in practical implementation. So the noise travels through this filter and then gets sampled. So we have a noise contribution here and a noise contribution here. So if we look at ZK in the case where we have noise, in the ideal case, if there is no noise, we can forget about this, right? And then the output is equal to the input. That's fine. Now we do have noise. So what can we say? Can we say something about this noise? Okay. Then we need to make certain assumptions on the noise. And the assumptions we have done in this course is to say that the noise is additive white Gaussian noise. Okay. And that is a standard assumption in the field. So and that's in a way is the worst kind of noise we can imagine. So if one then look how the noise travels to this, it's first filtered and then sampled and then scaled. And the combination of the filtering, sampling, and scaling implies that the noise component in Z, which is Nk, is a Gaussian random variable with zero mean, so the average is 0, and this as variance. Okay, and the variance is N naught, and N naught is what that specifies the level of the noise. In a way, the more noise we have, the greater N naught is, and then divided by twice the energy for the pulse. So EH here is the EH energy for HOT, and N naught over 2 is the power spectral density of noise. So I mean, at exams and so forth, we typically say, okay, the power spectral density of noise is N naught over 2, and then we specify N naught. So this is typically how these problems are phrased. Okay, any questions on this? All right, and then once we know what the input to the slicer is, it's what we transmitted plus some noise. We make a random assumption about the data that we transmit, and if these are if the bits we transmit are independent and equally likely bits, which is almost always the case, at least that's the common assumption we do, then all amplitudes are equally likely. The amplitudes take on values in this script A or curly A set, the symbol alphabet. And then one can compute the symbol error probability, which is the probability that A hat, K, which is the decision on the kth symbol, K here is the time index, is not, should be AK here, of course, not the hat. Sorry for this. So this is the probability that we make a symbol error. So probability that this is not equal to that. And then we are also interested in knowing what is the probability that the output bit is not equal to the input bit, and that's the bit error probability. And here, same typo, BI. Sorry. Okay. How to compute this? Well, first of all, as it turns out, we need to know the energy per symbol. And the energy per symbol is the energy for the pulse that we use times the energy for the constellation. So this is the energy for the pulse. This is integral. The energy for the constellation is the average amplitude squared. So take the amplitudes, square them, and take the average of these numbers, and then we get the energy for the constellation. If we have the transmitted power, it's related to the energy per symbol through this relationship. Power is energy divided by time. This comes from standard physics, I would say. So the question is to figure out what energy and what time to relate that to the power. And how it works is that the transmit power is the energy per symbol multiplied with the rate, symbol rate. Or, if you like, the energy per bit times the bit rate. Or, I don't know, the energy per apple times the rate of apples, right? Now, there are no apples being transmitted, but you see the idea, right? That if we assign energy to something and we push that out with a certain rate, that determines the power. Okay. So EB here is the average energy per bit, and then the data rate, which we care about, is the log 2 of m divided by t, and log 2 of m is the number of bits per symbol. Questions? Okay, let's continue. All right, and then we have Q functions, and then we can calculate the symbol error probability for baseband and passband PAM over a Gaussian channel. It looks something like this. So we see that the number of bits per symbol is here, or actually the number of amplitudes in constellation, which is, and the constellation is the amplitudes in A. So here, if we take the cardinality, we count the number of elements in the set, we get M. Okay, and then we see here we have M here also, and then we have ES over N naught, and N naught depends on the channel, and ES we have just calculated what that was. Okay, and we know that ES is ultimately dependent on the power of the transmitted signal. So power here helps us. Okay, so this is for the PAM. The corresponding for QAM looks something like this. We have PAM in one direction, PAM in the other direction. It's a two-dimensional constellation. We get something that looks like this. For high SNRs, when ES over N naught is large, for large ES over N naught, we can forget about the second term, because that's basically the square of the first term. So if we want to get a little bit of a simpler equations, one can just use this one for high SNR. For high SNR and gray coding, we can go from symbol error probability to bit error probability through this equation. In general, one has that the bit error probability is less or equal to the symbol error probability, but it's also larger or equal to the symbol error probability divided by log 2 of m. So this equation holds for all transmission schemes we can think about. For this particular, for PAM and QAM with gray coding high SNR, there is this equation, which basically means that the bit error probability is the smallest number it can possibly be. It tends to the lower bound here. Okay, yeah, I think that's it for the first 45 minutes. So let's take a 15-minute break.